Hey everyone, today we're going to be going over how to tackle this educator problem, balancing a BST. So this problem essentially has you implement 3 of the 4 AVL rotation functions. If you're working on the project's 1 AVL tree, it's going to be the exact same code. So if you're looking for some guidance there, stick around and we'll talk about the intuition and the code that can make these rotations possible. So let's first go over the rotations if you're unfamiliar. So enable the cursor here. I want to look first at these diagrams here. So you can see here that when we calculate the balance factor of each node, which is the difference in heights of the node's 2 subtrees. So for instance, this B node, right? This subtree has a height of 2, since this A and W are here. See, we have 2 nodes here in the subtree. So that subtree has a height of 2. 1 node in this subtree. So the difference in heights is 1. So this balance factor could be, say, 1. Now, if we, that by itself is fine. But this C, whereas one subtree just has a height of 1, the other one actually has a height of 3. And there, that makes C's balance factor a 2, right? Difference in subtrees or a -2, depending on how you look at it. The important thing is one of the subtrees has a height 2 larger than the other. And because of that, we want to balance the tree as a whole, centered around this C node. And the way we do that is here, we enter the left case, where there's 2 nodes to the left of the C node. That means we perform a right rotation. Similarly, if there were 2 nodes to the right of the node we wanted to balance, and there was more, like the height was greater in the right subtree, then we perform a left rotation. And both of them will give us, or will get us to this exact position. And let's quickly talk about what operations we have to do in order to reach this position. So let's start by talking about the right rotation. Here, we are given a node C, because this is the node we're actually balancing. And you can see that B becomes our new root node or our new parent node when we're done balancing. So let's start by saving this B node. So if you take a look, you can actually see that B's left subtree is left completely unchanged. So we don't have to do anything with that. The main changes come where B becomes the new root node, right? And we know C is greater than B because we go left from C to B. That means that C would have to end up in B's right subtree. So what we do is we make this node, or rather, yeah, we take this, what was previously the root node, and place it in B's right subtree as its right child. Now the thing is, there's already something there, right? Already this Y is there. So what we do is we take the Y and make it C's left child. So just to repeat, first, we store that B node here. That's the right child, or the left child of that C. So we store this B. Then we store this Y and overwrite it with this root node. Take the root node and we put it in place of the Y. Then we put the Y back as the left child of that old root node. Now, alternatively, what we can do to make our code a little bit more concise is store a pointer to the new root. I gotta stop drawing arrows, man. Store a pointer to the new root. Then update the root. So we have a pointer to this subtree. What we can then do is update the root's left node, because we already have a pointer to B, to instead point to this Y, right? And so effectively we have this tree here, the B, A, Y, W, X. And then we also have another tree here, like so. I know this isn't quite a tree here, but you can imagine it as 2 separate trees. And then from there, we can make B's right child equal to this C, right? So we essentially have B pointing like this to its right child. And you can see that we actually get the same structure we have here. Just imagine B as the root and it kind of, moving along to the right here, and to the left here. The left rotation obviously is going to be the same thing. So first we store the new root, which is going to be the B. Then what we'll do is we want to place A down here and assign X to be A's child. Again, what we can do to kind of save the space is actually to just make the X. So this is what we have stored. Is just make the X A's right child. And then assign B's left pointer point to A. And again, we reach the same outcome if you imagine B as our root node that will then return. All right, so now that we've gone over the conceptual left and right rotations, let's write them real quick. So with the left rotation, that's what we just went over. So first, we obviously want to identify the new parent. So I'll go node, new parent, and again, here we want to move to the part of the tree that has more nodes because that's where our new parent will be. So we'll just go node right. Remember that this left rotation corresponds to the right case. It's a bit of a misnomer. Then our goal is to swap the A to be the new parent's left node, right? So we can do that here. We can say new parent left equals the original node. But that will, of course, overrule the X. What we can do, again, like I said originally, we can store the X in a pointer, and then when we move the A over here, we can make the A's right child the X. But the easier way to do that is just to, right here, assign the original node's right child to be that X, which is the new parent's left node. Once again, what we're doing with that is we're effectively just making this point over here. We're making that point, that point down there to the X. So when the B eventually points up to the A, everything is tied up nicely. It's a little small here, so drawing maybe a little vague, but hopefully it did make sense with the larger explanation we did at the start. And then these rotations, so the function that calls them knows what the new root is, they should actually return the root. Sorry, by root, I mean the new parent, the new root node of the new tree. And I won't, I'll kind of gloss over the right rotation pretty quickly. Essentially, it's going to be everything flipped from the rotate left function. So for the right rotation, first we capture or we store the left node of the root node and make that the new parent. That's going to be the node we eventually return. Then we take the original node and make that its new left child to become this Y, the new parent's right node. So node's new now left node is going to be the new parent's right node. And you can see we're really just flipping the lefts and rights because these are just symmetrical transformations, really. And then last thing is we want to update B's right child to be that original node. So new parent right equals that node. All right, but we're asked to implement one more rotation here. And this one is actually the easiest. So the rotate left right, when does this occur? So this actually occurs in the left right case where basically you have a node and you have two nodes chained like this, right? I like how the nodes just get like bigger and bigger, but whatever. And basically the idea is that there's two more nodes on this left subtree than there is on this right. So we can say this is like a +2. And here there's one more node, or there's the height is one greater on the right subtree than it is on the left. So we can say like it's a -1. It might have been taught flipped in class. I'm a little too lazy to check at the moment. But basically, this one has more node, a greater height in this subtree. This node, the child, has a greater height in the right subtree. So we effectively end up with a shape like this that we want to balance. Now, it would be great if we could somehow transform this into a straight line of 3 nodes, right? Because then we can just call a left or right rotation and be done with it. And the way we can actually do that is by first looking at the bottom two nodes, right? So here, if we call a left rotation, so assume this is like a right case, right? If we were to call a left rotation on this, remember that this node, so if I just scroll up to the left rotation code, this node would become the new parent, right? Node.right, because this is a node that's passed in. This node will become the new parent. And so we'll end up actually returning the new parent with its left node subtree assigned to the original node. So if we were to call it a rotate left on this chunk, what we get is the new parent returned with node as its left child. And this still follows the properties of the BST, right? New parent is greater than node, which is why it's on its right. And here, node is less than new parent because it's on its left. So this still works. And now we've ordered them in a way so that we can just perform a right rotation on the root node and get back our fully balanced structure. So let's try that out. Here's drawings. So, like I said, we have a left-right case, which means that literally we have a root and then a node to the left and a node to the right. So on the node to the left, we want to call the left rotation. So rotate left, node left. And that's because we're essentially emulating a right case in that left node. I'm gonna draw it out again. We have a root, we have a left node and a right node. So we're essentially emulating the right case here. And so we call a left rotation. And because this left rotation will return this new parent, which will be this node, we actually want to make sure we assign the left node to be whatever is returned to it. Otherwise, it's just going to get messy. Essentially, we want to actually update this root and have it move up to where it should be. And so then at this point, again, because this is the new parent, and we've just assigned this node's left to the new parent, we end up getting this triple structure, which is the left case. So it calls for a right rotation. Okay, right? And here we can just pass in the loop itself. And that will give us the new parent, which will be this node in the middle here. And so we can just return that as the desired new parent. Let's run the code. Seems to have worked. Let's submit it. And all test cases have passed. All right, hopefully that helped out. If you have any questions, feel free to message us on Slack, which is probably what we're using at the time of you watching this. And good luck on Project 1.